This should be quite a quick little video. It's just talking about the four fundamental forces of our universe. We've talked quite a bit about gravity and electromagnetic force, and I think we're fairly confident and comfortable with those. The other two are the strong nuclear force and the weak nuclear force. I think we've probably already talked about those. I mentioned light. Remember, we talked about the fact that light is mutually reinforcing electric and magnetic fields, like my dance there, that can travel without a medium because it has space-time itself as the medium, so the forces reinforce one another. The electromagnetic force is much stronger than the gravitational force, so about 10 to the 20. Remember, the two constants are 9 by 10 to the 9 for electromagnetic and 6.67 by 10 to the minus 11 for gravitational. So the strengths of those two give us a basis of comparison for the other two. So the strong nuclear force is the strongest of all the four, but it's a very short range force. It acts only at very close range, as in inside the nucleus, which is extremely tiny. It's what explains why nuclei can stay together. You realize that the nucleus has neutrons, which have no charge, and protons, which have positive charge, and it's very tiny and compressed and pushed together. That doesn't seem to make sense because electrostatically, or the protons would repel one another and blow it apart. The reason they don't is the strong nuclear force. So the strong nuclear force is much stronger than the electrostatic force, and it is what holds the nuclei together. And without it, we wouldn't have matter at all. But because the electrostatic force is long acting, or long distance acting, and the strong nuclear is only very close acting, if you're trying to bring a proton into a nucleus, or if you're trying to smush two nuclei together, as you're doing in nuclear fusion, you have to overcome the electrostatic repulsion first before they get close enough for the strong nuclear force to then pull them together. Right? There's an energy barrier to be overcome. So the way we do that is by heating them up so that they're traveling fast and that they collide at speed. And when they collide at speed, they can get up and over that energy barrier and get close enough for the strong nuclear force to then hold them together. So that's why nuclear reactions require either to be initiated with neutrons, which is what usually happens, in order to get them to split. I'm sorry, I was talking about fusion and I think I said fission a minute ago. For fission in the sun, we need small nuclei to come together and join, so hydrogen or helium nuclei to join into helium or lithium. We need it to be the temperature of the sun for fusion to take place because we need them to have enough energy to overcome that electrostatic repulsion and get together. That's why it's very difficult indeed to have nuclear fusion on the surface of the Earth, because you need sun-type temperatures, 10 million degrees. And all known materials melt significantly before you get to those kind of temperatures. So what bottle do you put your reactor in? Turns out that you use a magnetic field bottle, but it's very difficult. And so we're still struggling to get fusion to work on Earth. Because you have to have that temperature, because you have to have that much energy to overcome the electrostatic repulsion in order to get the strong nuclear force attraction involved. Make sense? And then the weak nuclear force relates to nuclear decay, and we're going to talk about radioactivity and nuclear power and all of those things in our final week, next week. One way of describing it is quantum flavor dynamics. I just had to include that word when I read about it because it's kind of cool. Quantum flavor dynamics. But electroweak theory. So a theory about the ways in which the electromagnetic force and the weak force used to be the same force in the very, very early moments of the Big Bang and then separated out is the best way of explaining the weak force. And the weak force is quite a lot weaker than both the strong force and electromagnetism. So it's justifiably called the weak force. But it causes the breakdown of nuclei by either beta decay, So a neutron emits an electron, negatively charged electron, as a beta particle, and is left, turns from a neutron into a proton, positively charged. So you go from zero charge to zero charge. We'll talk about some of that next week. Or to breakdown of various other kinds of nuclei to fission and so on. So the weak force is related to radioactive decay and various kind of breakdowns. That's probably about as much as we need to talk about it at this stage. We certainly don't get into calculations with these forces, but we need to know that they're there and that they exist and that they're the only four forces. That all other forces are some kind of special category of these four forces. These are the four fundamental forces of our universe.